And here we are talking about units of K. We actually discussed this quite a lot in the extension packet, but thought I'd throw a question in here just so you can illustrate that. Told you what the rate law is. Rate is K times X times Y squared, so that's a third order reaction. Units of rate, always moles per litre over time. Seconds is always a good one to use. K we don't know, but our concentration, X is moles per litre, Y is moles per litre squared, so moles per litre times moles per litre times moles per litre. We can cancel out a moles per litre from the left with one of the ones on the right, and now we're left with what K has to be. Well, K's got to have seconds on the bottom, okay? And now you've got moles squared. Well, you don't want moles squared here for the K, so to get them down here they have to be on the bottom, and you've got litres squared on the bottom, which would have to be up the top for K to cancel out. So therefore K litre squared to cancel out those, over mole squared to cancel out those, over seconds to match up to the per seconds there. Another way of writing it, which is much prettier. All right, now we're moving on to the next factor that affects reactions, or rates of reactions, and that is temperature. We've studied how concentration affects it with the rate law. How does temperature affect it? So conceptually, when you increase the temperature for any system, the particles move more quickly. Now, reactions determine, as far as the rates of reaction are determined, because reactions have to start with collisions. And those collisions have to have the right orientation that we'll talk about later on, but they also have to have a minimum energy. Now, when you heat up the reaction mixture, the particles move more quickly. That means more collisions. And because they're moving more quickly, those collisions are going to have a higher energy. So let's see what we have here. Option 1. Greater fraction of collisions have sufficient energy to exceed EA. Well, that's yes, they have that higher energy, so that looks good. Reactant concentrations higher at higher temperatures? No, that's just silly. And collisions are more frequent at higher temperatures? Absolutely, that was the other thing we said. So the answer to question 9, 1 and 3. So the relationship between rate of reaction and concentration is the rate law, which varies for every reaction based on the orders. The relationship between the rate and temperature is the Arrhenius equation, which is the same for every reaction. The only thing that changes is A, the Arrhenius constant, which we don't worry about at A level, and EA, the activation energy, which we very definitely worry about at A level. The activation energy is the energy required to get the reaction going. Somehow you've got to have enough energy, which comes from collisions, to overcome that activation barrier, that activation energy hump. And so the Arrhenius equation relates the rate constant, K, which of course is associated with the rate, to a constant, to a temperature. So the relationship between the temperature and the rate via the rate constant. Now there's all kinds of fun calculations one can do with this. Some A-level teachers and boards do them, some don't, so we'll just go ahead and do these. And of course I threw in a couple of examples on the actual post-movie quiz when we dealt with Arrhenius, but let's do a couple more. Okay, so anyway, we've got rate constant at a temperature is this. So we know K, we know the temperature. Calculate the rate constant at a different temperature. So we need a different rate constant for the different temperature given the activation energy. Now what we could do is we could just say, okay, well I know at 400, I know the temperature, I know K, I know the activation energy. Put all that in and calculate A, and then I know A and the activation energy, so I can calculate K at this new temperature. The more elegant way to do it is via simultaneous equations. Just say, well, we got two sets of conditions for which log of A is the same and EA is the same. So log of K is minus a T1, K2 at blah, 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 T2. Now let us combine those equations after we've thrown in the values. So I've said K1 is the unknown at 410 Kelvin, K2 3.2 times 10 to the minus 2 at 400 Kelvin. Subtract those equations from each other, this equation minus this equation. So log minus a log is log of a quotient. Log of A go out. EA over R goes out, so I have minus 1 over 410 minus minus 1 over 400, so that's 1 over 400 minus 1 over 410. Throwing those values in, doing that subtraction, can sometimes be a little challenging for people. Make sure you see how it works. Anyway, one thing to worry about is units. I've been lazy by not putting them in here because it takes a while, but R is 8.314 joules per mole per Kelvin, which means activation energy also has to be in joules. I gave it to you in 41 kilojoules, so therefore we need to express it as 41,000 joules per mole. So now throw everything in. 1 over 400 minus 1 over 410 is this nasty looking number, EA 41,000, R 8.314. So now right hand side boils down to this, and we've still got this nasty natural log here. How do you get rid of a natural log? Well, it's just e to the power of x. So let's go ahead and take e to the power of x on both sides. E to the power of this, the e to the power of, and the log go away, so it just becomes k1 over 3.2 times 10 to the minus 2. E to the power of 0.301 is 1.35. Now simple multiplication, k1, 0.043 per second. Nasty maths, which is one of the things that makes people dread this whole thing, but it's fairly straightforward once you remove the fact you've got nasty maths. Another Arrhenius equation, even though it starts off in a weird way, food rotting about 50 times more rapidly. So in other words, the reaction at 25 is 50 times faster than the reaction at 6. And I'm asking for the activation energy. Well, anytime you see activation energies, temperature, you know it's going to be the Arrhenius equation. I like to, again, consider the Arrhenius equation at two different sets of conditions, both different sets of conditions here. So throw in what we've got. We know it at 6 degrees Celsius, which is 279. We know it at 25 Celsius, which is 298. So let's throw those in. Now again, let's combine those equations together to get rid of the natural log of a's. So we'll do k2 minus k1, log of k2 minus log of k1. So a log minus a log is a log of the quotient. Again, log of a's cancel out. Pull out the EA over R, and I have minus 1 over 298 minus 1 over 279. Now, I want the activation energy. I know R, I know the temperatures, I know the temperatures. Somehow I must know this. Well, let's go up to what the question was. The rate at 25, so that's the rate at 298, which is K2, is 50 times faster than the rate at 6, which is the rate at 279, which is K1. So what it's telling us is K2 is 50 times bigger than K1. Okay, K2 over K1 is 50. That's the ratio, 50 times more rapidly at 25 degrees Celsius, K2, than at 279 Celsius, K1. So now we can pop that in. Log of K2 over K1 is 50. EA is 142,324 joules. Usually express it in kilojoules per mole. Okay, so a couple of Arrhenius calculations associated with these with this material. A couple of examples I did in the movie part, and then another couple of examples here. Hopefully it makes sense. The big reason for worrying about the Arrhenius equation at A level is because it illustrates a fantastically convenient tool for handling data. A lot of times when you're studying two variables, the relationship between those variables will be some nasty mathematical one. Well, if you can somehow work with those nasty mathematical relationships so that you can plot the data in a straight line, in other words, get it to where the relationship between the variables is a straight line, then it makes it an awful lot easier to interpret your data, because it's much easier to work with straight lines than it is nasty curves. So we'll look at the Arrhenius equation, and I'm going to rewrite it a little bit. So got log of k. Well, k is one of the variables. Is activation energy over R? Well, for a given reaction, activation energy is a constant, and R, of course, is a big constant. T is a variable. So we got a variable is something times something to do with a variable plus a constant. Now, if I plot k against t, I get a disgusting looking curve. On the other hand, though, if I look at the nature of this, the whole left-hand side, call it y. So if instead of plotting k, I plot log of k, is on this right-hand side, some constant, EA over r, times not t, but 1 over t. So if I plot not t, but 1 over t, then I get this straight line relationship here, a constant times my variable, 1 over t, plus another constant. So k against t, yucky graph. Log of k against 1 over t, nice graph. Now that nice graph is going to have an intercept at log of a, so up here will be natural log of a, the intercept, and now the slope is going to be minus EA over r. Well, r is a positive number, EA is a positive number, so that tells me my slope is going to be negative. Determine k at different temperatures, plot log of k against 1 over t, you get a nice pretty straight line that has a slope of minus EA over r. Now in this particular question, we were told the slope is minus 5.25 times 10 to the 3. So there we are. Slope is minus 5.5 times 10 to the 3. Slope is also minus EA over r. So we pop those in, make them equal. Get rid of the minus sign, multiply both sides by r, 8.314 joules per mole Kelvin. And we get that the activation energy, 43,648 joules, or about 44 kilojoules. Continuing on with the idea of activation energies, collisions, and so forth. So which of the following statements are false? The higher the activation energy, the slower the reaction. That's correct, because the higher the activation energy, the bigger a hump there is for the reaction to get over, so fewer collisions will have that much energy, so therefore the reaction will be slower. Exothermic reactions also always faster than endothermic. Now, this is a point that I want to keep making many times during the whole course. You have kinetics and you have thermodynamics. Thermodynamics, you start, you end, you don't care how you got there. Kinetics, you start, and everything is about how you get from there to products. Exothermic and endothermic reactions are thermodynamic. They've got nothing to do with kinetics. Okay, if I use again a silly example, if I say when I go to work I start at my house and I end up at work, that's a thermodynamic. Start at house, end up at work. Okay, the distance between my house and my work is the distance. Okay, however, I could walk there, I could take a car there, I could go via London first, I could do all kinds of ways to get from work or home to work. That's the kinetic part. Okay, exothermic, endothermic is thermodynamics. Thermodynamics, nothing to do with kinetics. Therefore, exothermic reactions and endothermic reactions will happen at the speed they happen. You cannot relate the two of them. Finally, reactor molecules involved in collision that has a higher energy than the activation energy, the reaction will always happen. Well, that sounds good, doesn't it? You got the collision, it gets you over the hump. However, you've also got to have the right orientation of the molecules around. I like to say if you've got another reacting species, it has to be in the right place at the right time, otherwise the collision will go nowhere. So while that's half the case, it's not always going to happen.